All right, we are live. This is day 3 of me learning OpenGL, and today we're gonna be reading the shaders chapter. As mentioned in the Hello Triangle chapter, shaders are little programs that rest on the GPU. These programs are run for each specific section of the graphics pipeline. In a basic sense, shaders are nothing more than programs transforming inputs to outputs. Shaders are also very isolated programs in that they are not allowed to communicate with each other. The only communication they have is via their inputs and outputs. In the previous chapter, we briefly touched the surface of shaders and how to properly use them. We will now explain shaders and specifically the OpenGL shading language in a more general fashion. GLSL. Shaders are written in a C-like language, GLSL. GLSL is tailored for use with graphics and contains useful features specifically targeted at vector and matrix multiplication. Shaders always begin with a version declaration, followed by a list of input and output variables, uniforms, and its main function. Each shader's entry point is at its main function, where we process any input variables and output the results in its output variables. Don't worry if you don't know about what uniforms are, we'll get to those shortly. A typical shader has the following structure. Okay, so we actually did write a similar shader here. We have a basic vertex shader and a basic fragment shader, which we used in our previous chapter in order to put a triangle on screen, and after that we put two triangles on screen to make a rectangle. So here it says that a GLSL shader always starts with a version declaration. You have hash version and then the version number, which is exactly what we did before. Here you can see we have version and 330 core, and it's the same for the fragment shader as well as the vertex shader. Okay, did not mean to do that. Yep. When we're talking specifically about the vertex shader, each input variable is also known as vertex attribute. There's a maximum number of vertex attributes we're allowed to declare, limited by the hardware. OpenGL guarantees there are always at least 16 4-component vertex attributes available, but some hardware may allow for more, which you can retrieve by querying glmax vertex attributes. Okay, so here we have the number of attributes and gl get integer v, then you can do glmax vertex attributes, and then it will put how many attributes it supports in this variable, and then you can check that. This often returns the minimum of 16, which should be more than enough for most purposes. Let's actually do that and see how many we get. I'm gonna put it in main right before our render loop. Alright, so it says number of vertex attributes supported is 16, and that is the minimum amount. You will always have at least 16 attributes available to you. Types. GLSL has, like any other programming language, data types for specifying what kind of variable we want to work with. GLSL has most of the default basic types we know from language like C, int, float, double, uint, and bool. GLSL also features two container types that we'll be using a lot, namely vectors and matrices. We'll discuss matrices in a later chapter. Vectors. A vector in GLSL is 2, 3, or 4-component container for any of the basic types just mentioned. They can take the following form. N represents the number of components. Vec n, the default vector of n floats. B vec n, vector of n booleans. Okay, I did not know that. I knew about the float vectors, but I did not know about these other vectors actually. So bvec will give you Boolean vectors, ivec will give you integer vectors, uvec will give you unsigned integer vectors, and dvec will give you double component vectors. Okay, Most of the time, we will be using the basic vec n since floats are sufficient for most of our purposes. Components of a vector can be accessed via vec.x, where x is the first component of the vector. You could use .x, .y, .z, and .w to access their first, second, third, and fourth component respectively. GLSL also allows you to use RGBA for colors and STPQ for texture coordinates, accessing the same components. The vector data type allows for some interesting and flexible component selection using swizzling. Swizzling allows us to use syntax like this. So we got some vector 2 here and a different vector 4, and then we can do some vec x, y, x, x. So you can actually refer to the same component of a vector multiple times, and that's called swizzling. You can even do x, 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 and that will give you just the x component, and you can put that into another vector. Okay, interesting. You can use any combination of up to 4 letters to create a new vector of the same type as long as the original vector has those components. It is not allowed to access the z component of the vec2, for example, because it only will have x and y. We can also pass vectors as arguments to different vector constructor calls, reducing the number of arguments required. Okay, so if you are going to make a vector 4, you don't always have to supply four arguments here. You can actually supply a vector 3 and then a float, and it can actually make a vector 4 out of that. Vectors are thus a flexible data type that we can use for all kinds of inputs and output. Throughout the book, you'll see plenty of examples of how we can creatively manage vectors. Ins and outs. Shaders are nice little programs on their own, but they are part of a whole, and for that reason we want to have inputs and outputs on the individual shaders so that we can move stuff around. GLSL defines in and out keywords specifically for that purpose. Each shader can specify inputs and outputs using those keywords, and whatever and wherever an output variable matches with an input variable of the next shader stage, they are passed along. The vertex and fragment shader differ a bit though. Okay, the vertex shader should receive some form of input, otherwise it would be pretty ineffective. The vertex shader differs in its input in that it receives its input straight from the vertex data. To define how the vertex data is organized, we specify the input variables with location metadata, so we can configure the vertex attributes on the CPU. We've seen this in the previous chapter as layout location is equal to 0. The vertex shader thus requires an extra layout specification for its purpose, so we can link it with the vertex data. It is also possible to omit the layout location 0, specify and query for the attribute location in your OpenGL code via glgetAttrib location. But I'd prefer to set them in the vertex shader. It is easier to understand and saves you the OpenGL and OpenGL some work. Alright, that makes sense. We actually did this for our vertex shader, and this actually it's really helpful for me to go back and look at this diagram. Like vertex shader is always the first thing, so it gets its data from the vertex data that we set in our C++ code, and that's why it has this extra level of setup that we need to do. Okay, I gotta find this IP attrib. Oh yeah, so where is it? Oh, it'll probably be in our vertex shader. So this layout location is equal to 0 is actually the setup that we need for a vertex shader, but we don't need that for a fragment shader, because we need to tell the vertex shader where to start getting its location from, I suppose. But a fragment shader is just a next thing in the pipeline, so it will just get its data from the previous step. I guess that makes sense. The other exception is that the fragment shader requires a vec4 color output variable, since the fragment shader needs to generate a final output color. If you fail to specify an output color in your fragment shader, the color buffer output for those fragments will be undefined, which usually means OpenGL will render them as either black or white. So if we want to send data from one shader to the other, we'd have to declare an output in the sending shader and a similar input in the receiving shader. When the types and the names are equal on both sides, OpenGL will link those variables together, and then it is possible to send data between shaders. This is done when linking a program object. To show you how this works in practice, we're going to alter the shaders from previous chapter to let the vertex shader decide the color for the fragment shader. Okay, that's interesting. Because we know vertex shader comes before the fragment shader, we can actually specify some data here. In this case, we're going to specify the color, and then that's going to be input into the fragment shader, which it will use to render the color. So this part is the same. Here we're actually gonna do an out vec4 vertex color. Okay, this specify a color output to the fragment shader. Okay, this is before main. And then it's setting the vertex color equal to set the output variable to a dark red color. Okay. And then in the fragment shader, we can do an in vector color, vertex color. So the name and the data type needs to match. This is gonna be an out, and here it's gonna be an in. The input variable from the vertex shader, same name and same type. And here we are doing a frag color this rather than doing that. We can just use the vertex color that we got from the fragment shader. Sorry, the vertex shader. I don't know if this commenting will work. You can see we declared a vertex color. Okay, now our rectangle should be red, which it is. Alright, so that worked. You can see we declared a vertex color variable as a vec4 output that we set in the vertex shader, and we declare a similar vertex color inside input in the fragment shader. Since they both have the same type and name, the vertex color in the fragment shader is linked to the vertex color in the vertex shader. Because we set the color to a dark red color in the vertex shader, the resulting fragment should be fragments should be dark red as well. The following image shows the output. There we go. We just managed to send a value from vertex shader to the fragment shader. Let's spice it up a bit and see if we can send a color from our application to the fragment shader. Okay, now we have uniforms. Uniforms are another way to pass data from our application to the CPU on the CPU to the shaders on the GPU. Uniforms are, however, slightly different compared to vertex attributes. First of all, uniforms are global. Global meaning that a uniform variable is unique per shader program object and can be accessed from any shader at any stage in the shader program. Second, whatever you set the uniform value to, uniforms will keep their value until they're either reset or updated. To declare a uniform in GLSL, we simply add the uniform keyword to a shader with a type and a name. From that point on, we can use a newly declared uniform in the shader. Let's see if this time we can set the color of the triangle via a uniform. Okay, so this is our fragment shader. And rather than getting our color from the vertex color, we are actually creating a uniform. we set this variable in the OpenGL code. We have named it our color, and we're just gonna set that here. Okay, right now this uniform, I don't think this uniform is set to anything, so it'll just be black. Yep. We declared a uniform vec for our color in the fragment shader and set the fragment's output color to the contents of this uniform uniform value. Since uniforms are global variables, we can define them in any shader stage we'd like, so no need to go through the vertex shader again to get something to the fragment shader. We're not using this uniform in the vertex shader, so there's no need to define it there. If you declare a uniform that isn't used anyway in GLSL code, the compiler will silently remove the variable from the compiled version, which is the cause of several frustrating errors. Keep this in mind. The uniform is currently empty. We haven't added any data to the uniform, so let's try that. We first need to find the index location of the uniform attribute in our shader. Once we have the index/location of the uniform, we can update its value. Instead of passing a single color to the fragment shader, let's spice things up by gradually changing the color over time. Okay, so what is this doing? You got a time value, you got a green value which you are changing over time using a sine wave, and the vertex color location, GL get uniform location. Okay, GL use program and GL uniform for F. First we retrieve the running time in seconds via glfw get time, then we vary the color in the range 0 to 1 by using the sine function and store the result in green value. Then we query for the location of our color uniform using GL get uniform location, which we are doing right here. We supply the shader program and the name of the uniform that we want to retrieve the location from. Yep. To the query function, if GL get uniform location returns -1, it could not find the location. Lastly, we can set the uniform value using the GL uniform for F function. Note that finding the uniform location does not require you to use the shader program first. By updating a uniform does require you to first use the program by calling GL use program, because it sets the uniform on the currently active shader program. Okay, does it show the whole thing somewhere? Okay, where's our render loop? Input rendering, then we have active shader use GL use program right here. Then we can do our color changing thing, and then we're setting our uniform right here, and then now render the triangle. Let's add these comments in. I don't think we need the EBO thing which I commented out last time. We have the bind vertex array VAO and the draw GL draw arrays. Okay, here we're using GL draw elements. Matter. Okay, and then swap buffer, which we are doing here, GL bind vertex array. So I don't think we need this either. Okay, yeah, it's changing color over time. Okay, so let me understand this a bit. This is fine, we're getting a time value, and then we're passing that to the sine. This is a float. Okay, this is just controlling its time or frequency and stuff. And then we have the vertex color location. okay, so this actually GL uniform 4F actually tells that it's a vector 4 float type. We pass it the location of our uniform, and then we have to pass it 4 float types. This is the red, green, and blue value, and this is the A value, which is white, which is always 1. Okay, so yeah, that makes sense. The code is a relatively straightforward adaptation of the previous code. This time we update a uniform value each frame before drawing the triangle. If you update the uniform correctly, you should see the color of your triangle gradually change from green to black and to green again. That's exactly what we see. Check out this code here. As you can see, the uniforms are a useful tool for setting attributes that may change every frame, or for interchanging data between your application and your shaders. But what if we want to set a color for each vertex? In that case, we'd have to declare as many uniforms as we have vertices. A better solution would be to include more data in the vertex attributes, which is what we're going to do now. More attributes. We saw in the previous chapter how we can fill a VBO, configure vertex attribute pointers, and set it all in a VAO. This time we also want to add color data to the vertex data. We're going to add color data as 3 floats to the vertices array. We assign a red, green, and blue color to each corners of our triangle respectively. Okay, so first 3 floats are gonna be the position, and then the next 3 floats are gonna be the color of that vertex, and then it's just gonna be position, color, position, color, position, color. Since now we have more data to send to vertex shader, it is necessary to adjust the vertex shader to also receive our color value as a vertex attribute input. Note that we set the location of the A color attribute to 1 with the layout specifier. Okay. So we already had this, a position at location 0. Now we also need to get our color data, this thing, and we are setting it to layout location 1. Okay, let me just add this, including the comments. So this is our layout location 0, which gives us the position. And then we need to add layout location 1, which will give us the color. This is our color. Okay, this is the older one. Output color potential. GL position, we are already setting that. We're getting a pause. Okay, why does it do that? Comma 1. It's actually kind of same. Our color will be equal to A color. Our color. Will be equal to A color, which we are getting from our array. Cool. Since we no longer use a uniform for the fragments color, but now use the our color output variable, we'll have to change the fragment shader as well. Yeah, so here we are using this uniform. Since we're not going to be using that anymore, I'm going to comment out this uniform stuff. and here all we need is the our color in vec3. Okay. And here it is just using frag color equals our color as a vec4. Alright, I actually need to change my vertices array. Okay, so this is actually the rectangles. Let's edit this. This is gonna be completely wrong now. So I don't know what this is gonna show. Yep, it's completely wrong. So for that we actually need 0, 2, and 4. And I guess that's it. Yep, that's a triangle, but it's still not showing the correct colors. Since we now have more data to send to the vertex shader, we actually need to adjust our vertex shader. So we have added location 1. I've added location 1 here. And this is our fragment shader. Because we added another vertex attribute and updated the VBO's memory, we had to reconfigure the vertex attribute pointers. The updated data in the VBO's memory now looks a bit like this. Rather than just having the XYZ, 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 we have also added our RGB data in between these. And this is like one vertex. So, okay. It's under vertex attribute pointer. Attribute color attribute. Okay, so now we actually need 2 of these. GL vertex attribute pointer, this thing. We can tell OpenGL how it should interpret the vertex data per vertex attribute. Here this is our 0, that means the position of the vertices. We need another one which will be for the color of our vertices. Okay, I'm just gonna copy this, but I'm actually gonna type out the GL vertex attribute pointer because I want to learn. Okay, so first is I guess the position 1, and then 3 vertices. Data type is GL float, and this, what is this? GL false. Finally, this is actually now 6 floats instead of 1, so rather than being 3, it's gonna be 6 times the size, 6 times the size of float. And then this is gonna be void pointer, cast to void pointer 0, but now it's actually doing 3 times size of float, which will actually offset it by this amount. Okay, so I guess that kind of tells it where to start. And rather than doing 0, we're doing this. Okay, it's not correct. Using a bracket. Okay. Yeah, so this is our position attribute, and this is our color attribute. Okay, will that work? No, it does not. 0, 1, 3, GL float, GL false, 6 times size of float, 6 times size of float, 6 times size of float, it's the same. void 0 void pointer 3 times size of float. Okay, I don't think there's a problem here. Okay, these are the vertices. I don't think there's a problem here either. Okay, so is it going to use the indices on this vertex array, or is it going to use it on something else? Because if I just need to tell it to use the first, the second, and the third, then it's going to look something like that. Yeah, okay. So actually, when you are trying to define these indices, rather than looking at this, if it has more than just the position data, like in this case it also has the color data, then these indices is not going to match with these positions. You actually have to look at the whole thing, which is like all of these attributes combined for one vertex. So this is the first vertex, the position and the color. So this will be 0, this will be 1, and this will be 2, which is exactly what we have right here. But there's still the problem that we're not getting the correct color. Okay. Since we no longer use a uniform for the fragment color, but now use our color output variable, we'll have to change the fragment shader as well. I already read that, and then with this, the first few arguments of GL vertex attribute pointer are relatively straightforward. This time we are configuring the vertex attribute on attribute location 1. The color value have a size of 3 floats, and we do not normalize the values. Since we now have 2 vertex attributes, we have to recalculate the stride value to get the next attribute value. For example, the next x component of the position vector in the data array, we have to move 6 floats to the right. I guess that's where this comes in. 3 for the position values and 3 for the color values. This gives us a stride of 6 times the size of a float in bytes. Also, this time we have to specify an offset for each vertex. The position vertex is first, so we declare an offset of 0 here. The color attribute starts after the position data, so the offset is 3. Okay, this makes sense, but for some reason it's not giving me the color. Is it throwing any error? Okay, it is. Shader vertex compilation failed. Assignment of incompatible types. Okay, so there's an error in the vertex shader. That's handy. So our color, okay, well, wait, what am I doing? We need, I think we need out color. Wait a sec. Out vec3, our color. Okay, it needs to be vec3. Let's go. Yay, we have our triangle. Okay, so it's also saying that why does it have this gradient? Because it does something called fragment interpolation in the fragment shader. When rendering a triangle, the rasterization stage usually takes in a lot more fragments than the vertices originally specified. The rasterizer then determines the position of each of those fragments based on where they reside on the triangle shape. Based on these positions, it interpolates all the fragments shader output input variables. Say for example, we have a line where the upper point has a green color and the lower point has a blue color. If the fragment shader is run at a fragment that resides around 70% position of the line, its resulting color input attribute will be a linear combination of green and blue, to be more precise, 30% blue and 70% green. Okay, so it's saying this vertex is defined as blue and this vertex is defined as green, so everything in between will actually be interpolated. That's how it will calculate what color all of these pixels should be. So now we're gonna write our own shader class. Writing, compiling, and managing shaders can be quite cumbersome. As a final touch on the shader subject, we're going to make our life a bit easier by building a shader class that reads shaders from disk, compiles and links them, checks for errors, and is easy to use. This also gives you a bit of an idea how we can encapsulate some of the knowledge we learned so far into useful abstract objects. We will create the shader class entirely in a header file, mainly for learning purposes and portability. Let's start by adding the required includes and by defining the class structure. Okay, so we're gonna have a class called shader. Is it just gonna be a header file? Yeah, it's just a header file. Okay, we already have pragma once. We're gonna need to include glad. Glad slash h. Why is it throwing an error? Oops. Okay. We need string, fstream, sstream, and iostream. Wait, is these here? Yeah. Okay, we have our class shader. We're gonna have some public members. Okay, first we're gonna have a program ID, which is gonna be an unsigned int. And then we are gonna have a constructor that reads and builds the shader. Okay. So what does it need? It needs a const char pointer with xpath. Const char pointer. Okay. And it needs a const char pointer fragment path. Okay, it's actually not have it does not have a body. Void use. We're gonna have some utility functions. Void set bool. It's gonna need a const standard string address of name, standard string reference name, and a bool. I think let's just follow it, and a bool value, and we're gonna set it as const. Okay, void set int. It's gonna be similar, right? And it's gonna need a string and a value. Okay, I guess I can just duplicate that then. Set bools and set float. Okay. We use several preprocessor directives at the top, blah blah blah. The shader class holds the ID of the shader program. Its constructor requires the path file paths of the source code of the vertex and the fragment shader respectively that we can store on disk as simple text files. To add a little extra, we also add several utility functions to ease our lives a little. Use activates the shader program, and all set functions query a uniform location and set its value. Reading from the file, oh my god. This is the shader class holds the ID. Okay, I already read that. Reading from file, we're using C++ file streams to read the content from the file into several string objects. Okay. Retrieve the vertex fragment source code from file path. Standard string, vertex code, standard string, fragment code. IF string, V shader file, IF stream, F shader file. Ensure I stream objects can throw exceptions. So dot exception, the std stream fail bit or bad bit. Okay, I don't know what this means. And then it's doing a try block here. Open file, open both of these, and then we got string stream. Read files buffer contents into streams. Okay, close the file handlers, convert stream into string. All right. Okay, what the hell is this? And if that fails, we can do a catch. This is V shader code and fragment shader code. Is this just one function? I think it is. Okay, let's just copy it into our shader. Do they want to put this in the header file? Compile the shaders. So we got unsigned int vertex and fragment success. It's similar to what we did before. We're gonna create the shader, give it the code. It's gonna give us an ID. First we're gonna check if it's success or not, in which case we're gonna throw an error. We're gonna print it to the console. Then we're gonna get a shader program ID. We're gonna create this program. We're gonna pass it the vertex and the fragment shader IDs, and then we're gonna do a link program, print linking errors if any. It's the same as before, and then we're gonna delete the shaders. Okay, this part makes sense. The use function is straightforward. We're just gonna call use program on it. Okay. For this, we're gonna just do GL uniform 1i, GL uniform 1i, GL uniform 1f. Okay, I guess. So it takes a name string and then it converts it to a C string and passes that to GL get uniform location. Here we have the ID. This is ID. Oh, okay, it will actually be up here. It's this, the program ID. Okay, yep. And we have the int value that we actually want to set. Okay, no. And there we have it, a complete shader class. Using the shader class is fairly easy. We create a shader object once, and from that point on from that point on, simply start using it. Okay. Shader, our shader, and then we give it the path to our vertex shader and the fragment shader. Wait, really, is it that easy? So all of this stuff, wait, is it giving an error? Yep, don't need that. Oh, it's a similar for fragment shader. What the hell? So this is actually incomplete. I'm gonna need to do this stuff for the fragment shader as well. I guess I'll just copy it from here. Check compile errors. Wait, what? It has a check compile errors. Utility function for checking shader compilation. Okay, this is a completely different thing. I'm going to copy this class. So it actually has a check compile errors function. We've already seen this. And the use, I guess the rest is the same. It just has the vertex and the fragment shader both written here. Okay. And then finally we have this. Anything related to the shader, we don't need to put that here anymore. Maybe we can put these in a separate text file. All of this shader stuff will now go away because we don't need to do any of this. We don't need to do the linking shader anymore either, or checking for this or delete. Okay, yeah, all this goes away. Now all we have to do is, I guess, include the shader, which for me will be that. Right. Cool. Okay. So here we are actually building and compiling our shader. We're gonna create our shader object, and it's actually gonna give it these two files as arguments. Okay, where is it doing that? Before the vertices array. Okay. And then we'll just need to call our shader.use rather than this. Oops. Cool. Now I actually need to create these two shader files. Shader vs, shader fs. I just need to add a text file. Okay, I think I'm going to directly do it from here. Okay, so this is a vertex shader and a fragment shader. Now we need to get rid of all of these. Wait, what is .fs has color syntax highlighting? Okay, I did not expect to work on first try. Alright, so we don't need this anymore. And yeah, that's it. Okay, so how long has the stream been going? Okay, 52 minutes. So I think that's about it. We did the shaders chapter. If you actually want to see this stream, you can go to youtube.com/codestrum. That's where I put all of my previous streams. So if you want to watch in sequence the day 1 and day 2, you can find that on YouTube. All right, see you, bye.